Thanks a lot, Nathan. Can I go on? Right, so I'm going to talk today about how to bridge the gap between particle physics and cosmology. So the idea is that how can we import basically techniques and models that have been used in the last 50 years in particle physics community and apply that to cosmology to systematically improve the modeling of galaxy clustering and to basically get more information from the current data sets that we have. So the introduction, I'm going to start with the introduction, then I'm going to move forward towards the two-loop EFT that I've been working on. Then I'm going to talk about how to maximize the information extracted from galaxy clustering using multi-tracer techniques. I'm going to talk about the randomization group for LSS, which is basically trying to think about how things change in scale in cosmology and how we can basically import those RG techniques from high-energy community and apply that to galaxies. Then I'm going to move forward talking about cosmological tensions and models I've been working on. And finally, if I have time, I'm going to talk about gravitational waves. That's a side project that I have intensely been working on in the last 5 years as well. Right, so let me start with the introduction. So the common lore is that we have amazing data sets coming, right? Like we have CMB data, Planck, ACT, SPT, that basically have been providing amazing bounds in cosmology and amazing set of information that we can use to extract basically cosmological parameters and test models. Also, in the LSS side, we are very excited because we have DESI with new data release that they just had. Also, Euclid, DES that have been around in the last 10 years, KIDS, LSST, and Spherics. So we're very excited. We have a lot of data, and the common lore is that we have super precise data. So the point also is that when we have this amount of data, we have new things coming, new tensions arising. So the common you probably heard about the WA, W0, dark energy setup that we have been with DESI. So this is the new DESI release. Also, we have here, I'm just catching also DESI, which have been showing some tensions in between CMB data and LSS data. We also have the problem of neutrino masses, also after DESI release, and also the common H0 tension in between supernova data set and CMB. And also here, the old, not so exciting anymore, SA tension in between, sorry, can you hear me? In between Lansing probes and also LSS and CMB. So we have this set of tensions arising, and the question is, okay, after having this amazing data, we also should be able to provide precise theory. So the question I'm going to try to address is how to provide precise theory modeling such that we can use this data in a self-consistent way. This is the main focus of this talk. So the question I have in mind is, I have two things in mind. First, how can we provide model-independent tools that we have been learning in the last 50 years from the high-energy community, and how can we apply these QFT imported methods to describe endpoint functions and the fields in large-scale structure? Can we import these effective field theory techniques and apply that to LSS? And what I've been pushing on is how to move forward to higher loops to get more information, and also use these RG, these randomization group techniques, also to try to get more information from higher loops. So the second part of the talk, I'm going to talk about models, some models I've been working on and that I'm very excited to test in current data set. So let me start with structure formation. So the general objective that we have when we think about LSS is to describe endpoint functions of galaxies. So I'm just showing, flashing here, the two-point function, and then you can construct basically a probability density like of how much frequency points you have here as a function of the distance of those points, and you can construct the two-point function. So we have a galaxy map, and we can take cross correlations. So of course, like this is the two-point function, but we can think about generic endpoint functions of galaxies, and this is the main object I'm going to try to model here in this talk and focus on. So there are two main perspectives when you work on this field. So you can either be an experimentalist in which you try to push this line. So what I'm flashing here is the power spectrum as a function of k. And you can either try to push this line here, this vertical line, to this side, because on small scales, so here are small scales, on small scales we have quite narrow error bars, but on large scales the error bars are quite large because we have basically just volume limitations. So we, as an experimentalist, normally we try to push towards larger scales, larger volumes, right? And here in this region, theory works quite well because everything is linear and is well approximated by linear theory. So as a theorist, which is my approach, I try to move in the other direction, which is trying to use basically smaller modes, like basically higher case here, and understand this theory. But the problem here is that theory becomes mildly nonlinear. Things become nonlinear on small scales, and it becomes hard to model. So the two approaches, you can either try to get more data and make the error bars in this side narrower, or you can basically try to improve the model, like the modeling here on the small regions, and focus on how to get information also from small scales. And also something that we want is something that comes from first principles, right? We don't want just, slopey fitting functions for this, because for the two-point function, it might work quite well. But when we think about generalizing to higher order endpoint functions, and we are in the stage of using the three-point function, so here I'm flashing the three-point function, and you see like it becomes more complicated, right? So we want something from first principles that is able to provide a generic endpoint function prediction for galaxy clustering. So also the two-point function, the three-point function, and generically a field level prediction for galaxy clustering. So the framework that we have that we use for this is what I call like here the smoothed equations of motion. So the equations of motion that describe how matter clusters on large scales are basically fluid equations, so continuity equation that I show here, and Euler's equation. So this one basically tells you how the density, the overdensity, changes as a function of time. And you see on the right-hand side, there's a coupling, a nonlinear coupling between density and the velocity divergence theta here. So the second equation tells us, it's Euler's equation, tells us how the density, how the velocity changes as a function of time. And again, you have a nonlinear coupling between velocity and velocity. So the coupling here is given either by alpha, this alpha coupling here, or this beta coupling here. So the way we find to, can either, neglect the right-hand side here and so get the linear solution from the left-hand side equals 0, or you can aim for some perturbative solution in which we expand the density here, or the velocity if you want, as some powers of, like you basically split space and time as some powers of the scale factor A and delta here. So this works pretty well for Einstein de Sitter universe, and we checked in simulations that it also works on beyond Einstein de Sitter universe, which is our universe. And you see that basically you can split space and time, and you use these ansatz of this perturbative delta n, you plug this ansatz with some generic function f, this kernels f, back to this equation. You know the shapes of alpha, you know the shapes of beta, and this basically fixes these functions f you have here. Right, so you take these ansatz, you plug back here, and you find a systematic solution of a generic delta n for this fluid equation. So this is a way to move towards a smaller scale.
So why is this ansatz justified?
Well, this ansatz, it's just a convolution of delta ones. So you're just thinking about interactions of linear legs here that basically give you a nonlinear solution. You see, like it's just a generic kernel f here, and basically it's a convolution of different delta 1 legs, linear solutions, and imagine these delta 1s interacting and giving rise to nonlinear modes.
I just don't understand why there can't be functions of tau. Why
the functions of tau here?
Why does it factorize into a function of x?
Okay. This is a very peculiar thing about this equation, that if you use an Einstein de Sitter universe, this factorization works pretty well. So you can. Why? Well, it's just, you can see that in this case, A for an Einstein de Sitter universe basically the growth factor evolves as A, and when you plug this back here, you can basically figure out that this is a solution for an Einstein de Sitter universe. It's just one solution case that you have.
I agree it's a solution. I just don't know why it's the most general solution.
Because it's basically the case in which omega m equals 1. So if you take omega m equals 1 here, basically this factor goes out. I mean, you can write this term down as some products, and it's something that shows up.
Okay, thanks.
So for an Einstein de Sitter, this works pretty well. This factorization works pretty well. For generic lambda CDM universe, you have to test in simulations, and we have tested that this factorization works pretty well at sub-percent level. So it's a generic thing that we test. Okay, we assume this is true. This is true for Einstein de Sitter. We assume it's true for other cosmologies after testing in simulations. Okay? Right, so when you try to come up with these perturbative solutions and you calculate loops with these generic delta n's, you can, of course, take contractions of these delta n's and compute one loop corrections, and you can compute two loop corrections, and this is something we have done to extend these to 3 loops. So we extended to 3 loops. And what you see here, okay, the black line is the linear solution, and in blue you see the 3 loop contribution, in red the 1 loop, and in green the 2 loop contribution. So you see that already there's something systematically weird in this expansion, because you see that the 3-loop contribution is actually larger than the other loop contributions. So you expect from a Taylor series that the terms converge, but you see that higher loops actually can be larger than lower loops. So there's actually something weird here, and this something weird is what we call like the lambda dependence. So this lambda dependence, I'm just showing the 3-loop contribution as a function of the cutoff you put to compute these integrals. Because when you evaluate those integrals, you have to set a cutoff, either numerically or physically, intuitively. You have to ask what's the limitations of these fluid equations, right? So a UV cutoff. And what you see here on the right is that there is a strong dependence of those loops on the cutoff you put by hand here to evaluate this. So of course, there's a cutoff dependence that has to be removed. And in this case, it comes from a very simple physical intuition that's the limitation of this fluid description, right? Because we know that on small scales, we have shell crossing, so fluid particles cross each other, and this fluid description breaks down. So of course, we don't trust this fluid description up to very, very small scales. We have to set a cutoff by hand, and basically this lambda you put here, in which it can either be a numerical cutoff that you use to compute things, or you can think about a physical cutoff that's a limitation of this fluid description that you have. So after putting by hand this cutoff here, you can ask yourself, what's the most general thing I can also include that cancels off this lambda dependence? And this is what we call counterterms in the context of high energy physics. So after adding these counterterms, which basically are provided by the symmetries of the problem, so you basically consider higher powers in derivatives of the fields, and you add counterterms here that also depend on lambda, such that this depends on lambda, this depends on lambda, exactly in the same way to counterbalance how this depends on lambda, and delta becomes something that's lambda independent. So the idea is that you introduce by hand this cutoff, and also exactly the terms that cancel out this lambda dependence, such that on large scales, this fluid description works pretty well again. And the physical meaning for those counterterms are actually very intuitive. They're just corrections that expect in the case of fluid descriptions from the sound velocity, right? So you can expect the leading order description just being a sound velocity. So the first leading counterterms is going to be associated to some k-square contributions, so some derivative contributions that come basically from how waves propagate in this fluid, exactly as we expect. So after accounting for this lambda dependence and systematically adding this lambda dependence, it comes actually from a very simple physical intuition. I'm just flashing here a Van Gogh picture.
So you put a high energy cutoff, but so when you have a fluid description, in principle, you have an expansion in derivatives. And from that point of view, you have an energy scale. But the expansion in derivatives can be done, you can put, for instance, shear viscosity and bulk viscosity.
Exactly.
And that will give you a better approximation.
So what I'm not showing here, but in the second equation here, you also have a sigma ij contribution, right? That comes from
yeah.
So exactly what I'm adding is basically the terms that are allowed in this sigma ij by the symmetries of the problem. So what I'm doing is modeling this sigma ij, the first term being the sound velocity, as you would expect from sigma ij, right?
Yeah, so then I don't understand what is the loop contribution that you're talking about.
So the loop contributions I'm talking about is, okay, this fluid description works pretty well on large scales.
Right.
And you see here that you have a nonlinear coupling, right?
Mm-hmm.
So you have a nonlinear coupling between two legs. So you have theta and delta, or theta and theta, and those are linear. You can, in the first stage, plug in this.
Oh, I see. So loops for the
loops come
from the sources.
Loops come from the interactions, basically, you have here.
But related to the sources, not to the higher order derivatives.
No, loops come, you can either, when you add higher order derivatives, then at higher orders, those are also going to have loops, right? So it's, of course, at higher loops, these higher derivative terms are also going to contribute with second loops, third loops, right? But this comes just from the nonlinear coupling here.
Okay.
And it's important to make clear here that those loops are not quantum loops as in the
Yeah,
usual
that
case.
was my
This
confusion.
is something, I mean, normally when we think about loops, I mean, but classical physics also has loops, right? The integrations here are not over, many off-shell lines that we have, but it's just over multiple realizations of the universe that we have. So those are stochastic fields, right? So when you take
Okay.
the expectation value here of, so when you take the expectation value of these delta n's and with another delta n's, so what we're integrating over are basically different realizations of this field, right? Different initial conditions for this field.
Yeah, so, so the expansion in derivatives, that would also imply, in principle, higher order, quantum loops in principle, but...
Yeah, those also add quantum loop, quantum, nothing here is
Yeah.
quantum. Just to make clear, we are on scales. When we think about K here, we're thinking about close to horizon scales, right? We're not thinking about small scales.
Right.
Right? So we're not thinking about, these are basically halo scales. So there's no quantum, nothing quantum here. Okay? Right, so this systematic description is something that Van Gogh knew already because this just comes from separation of scales, right? So when we think about large scales, you can see fluid lines in this picture for modes case, but when you use a thick brush to paint it, you don't care about, the thickness of the brush, right? You can basically see fluid lines here despite having very thick brush. Yeah, question?
So it sounds like actually you're assuming separation of scales and enforcing that on your equations. Did I get that right? Because there are many theories where you don't have separation of scales, right? Like in the RG, if the cutoff is relevant, then you absolutely depend on the...
I totally agree. But in this case here, you can test in simulations again, right? You can just assume this separation of scales give you this derivative expansion, and you can just test up to which scale this derivative expansion works on, right? And this test you can do, you run simulations and you know exactly when it fails, and this is something you can systematically check.
Okay, so it was verified in simulations and then
verified.
Enforced on the equations.
Well, on
it's not a result of the equations.
Of course, if you go to very large scales, this separation of scales should work, right?
Not necessarily. Sometimes the cutoff is relevant. In the RG sense.
But on very large scale, linear theory works on large scales. This definitely works, right? So you can...
I don't know your system is the point, right? But not for all systems.
Well, this is, the whole universe we know is linear on large scales. So you can systematically move towards smaller scales and see when this expansion in derivatives fails. And this is exactly when fluid lines cross each other and you have shell crossing. So this is something we verify in practice.
Okay, thank you.
Okay. Right, so after accounting for these cutoff contributions, what I'm showing you here, this P with a bar on top, is after summing the counter terms. So when you add the counter terms, we see that the one loop contribution becomes the most relevant one, and then you systematically restore what you expect. The second loop contribution becomes the second one, and the third loop contribution becomes the smallest one. So after adding these lambda contributions, everything goes as you expect, and you restore the Taylor expansion, naive expectations that you have. Okay? Well, here you have something related to the BAO wiggles as well, right? And so this just comes from the BAO, the ratio. So this is, okay, on scales of order 0.1, you have the BAOs.
I don't know what that is, sorry.
The baryonic acoustic oscillations. So this is exactly where you have the BAO, and that's why you see these kind of features on these scales. So this is the same wiggles you see in the linear case. You see some wiggles here as well, right? For the linear case. So those are the baryonic acoustic oscillations that you have.
I'm missing something basic also. How do we fix these functions f?
So these functions f are fixed by plugging these ansatz back here. So these f are basically given as products. So those are just products of alphas and betas that you have here. So this f is a general, you can find this as a recursive relation as these alphas and betas that you have here. And those are just ratios of momenta, P1 and P2.
Is it clear that if you continue this expansion, this cure that you have for the third loop will continue to work in higher orders?
Sorry, what do you mean?
So you have a cure here that is adding these terms that you add in the next slide, right?
Yeah.
is it clear that this will continue to work?
So you know that the derivative, you can know exactly by the symmetries of this, the stress energy tensor that you add here, exactly which terms you add.
Mm-hmm.
And this is something, again, you test in simulation. So you add those terms, and you see up to which scales it works. And this is something we have done as well.
Okay.
Right, so moving forward. Okay, so there's another important ingredient here we are missing, which is what we observe is not actually matter. So the fluid equations I was showing you describe how matter evolves in large scales, right? But we have, what we observe is not actually matter itself directly, but we observe something else, which is the galaxy density field, right? We have barons in the universe. So we don't exactly observe dark matter itself, but we observe tracers of dark matter. And again, we can use the symmetries of the problem. The symmetry here is GR, which states that everything should come as two derivatives of the gravitational potential, phi g, to relate both things. So to relate how delta G, the galaxy density field, relate to matter, we can use the symmetries of the problem. So take contractions of this tensor here, constructing what we call an OPE. So we have an operator product expansion of this object here, taking contractions of this, and construct a bias expansion. So this is what we call the bias expansion, in which we have bias parameters BO here associated to different operators that you construct on top of contractions of this object here. So to relate both things, what we observe to something we have a fluid description, we use the symmetries of the problem and take contractions of this object as we do with Lego pieces, right? So just in a nutshell, this operator product expansion is something that you can take either a contraction with a Kronecker delta here and have something proportional to delta. So I'm just using Poisson equations, so two derivatives here of the potential give me something like delta, and this square gives me delta square, and you can, of course, take the other contraction you have here, delta ij and delta ij, to have something what we call the Galilean operator, so this G2. And in this operator product expansion, we have what we call composite operators. So we have quadratic operators of the field evaluated at the same point. So this strongly depends on the lambda scheme that you put, basically, on the cutoff that you add by hand. So again, you have a linear theory, and you have quadratic and cubic operators, and those receive contributions from very small scale physics, right? So again, you have to add a cutoff here and regularize this theory. Okay? So.
Sorry, can I ask a question? Henrique, can you hear me?
Yeah.
Could you go back for a second to where you defined epsilon on the previous slide?
Oh yeah, here. Sorry. Yeah, here.
So what is epsilon?
Right, so there is another piece I didn't comment on, which is stochasticity. So there are small scale fluctuations that in different realizations of the universe, you're going to have different small scale fluctuations that can add basically large scales that can basically interact and give you large scale corrections. So this is what we call stochasticity. This epsilon here is what we call stochasticity. And you can think about stochasticity, the leading terms of stochasticity being what we call the shot noise term, right? So basically, the leading contraction here would be a flat contribution on large scales, which is what we call the shot noise contribution.
Okay, and then just to back up a second, are you thinking of this bias thing as another implementation of EFT, or are you thinking of it as qualitatively differently than than essentially the EFT that you talked about with matter only?
I'm thinking about exactly the same implementation, but different in the sense that new operators are allowed here. So in the case of matter, matter is a trace of matter itself with some of those bias coefficients fixed to 1, right, and to 0, basically. So what I'm thinking about is a generalization of the matter case in which we have different bias coefficients BO, in which we have more general operators O that are allowed here. In the case of matter, we have equations of motion that fix many of those bias coefficients. It's basically the trivial case.
Okay, so then in an EFT perspective, the fundamental objects are no longer the matter. The on large scales, and the IR limit, the galaxies become the fundamental objects. Is that the way you're thinking of it?
So we still need the equations of motion to determine basically, because at leading order, this delta I, delta J of phi is we have to relate these to matter, right? So what I have here is a relation between this delta I, delta J, phi, which relates to matter itself. So for this delta on the right-hand side of this part here, using Poisson equation, we still have to use these F and G kernels to basically set the evolution of delta itself. So we still need the F and G kernels to set the evolution of delta.
So you need quarks and hadrons at the same time, basically.
Well, for the quarks and hadrons, I'm not interested in specifically in the quarks.
No, I'm saying that the matter is like the quarks and the galaxies are like the hadrons, right? But you do have, is that a fair
You're thinking about,
analogy?
okay, you're thinking about collapse structures, kind of this in this.
Yeah.
So I'm just, the main ingredient here is, you can think about, okay, I see your point. You're thinking about matter as basically the main ingredient in which the symmetries of, okay, the equations of motion fix here the kernels, and you use these components to fix the bias. I agree with this.
Okay, sorry, I've taken up enough of your time. Thank you.
Yeah. Right, so the state of the art is that after using this bias expansion, you can basically let these B parameters here free and fit in data. So those B parameters that you have here you can consider them as nuisance parameters that data is going to tell you. So for different galaxy sets, these B parameters are different, and you have to marginalize over these Bs to get a correct.
Can I ask a question? So this OP is an ansatz, right? It's a phenomenological ansatz. There's no...
Well, it's not an ansatz in the sense that gravity is the symmetry of the problem, and this OP is every contraction of this del I, del J, phi you can have. This OP is basically constructed on top of gravity symmetries, which are just del I, del J, phi. So this OP that you see here on the right-hand side are basically contractions of this object del I, del J, phi, which is what GR fixes for us. So you can either have at leading order this term, at second order you can only have two operators. So it's not an ansatz in the sense that we are using the symmetries of the problem, which is GR, to set this OP.
Okay. I'm confused because whenever I hear talks about this bias, I always thought it was something you have to fit and it's an ansatz.
Right. So
why is it just a product of B times O and not some smearing over tau?
I have to say that there are different approaches people take in the community, and people will call bias different things depending on the talk you are and depending to who you're talking to. So in the community, there are some people that are going to...
New Year.
Hello? Hey, yeah?
Sorry.
Okay. So depending to who you talk to, this bias will be people in the past used to take this and this as just a simple ansatz. And you take just simply delta, delta squared, delta cubic. But as time evolved, it became clear that it was something else in the story. And this something else was these other kind of operators that emerged. You can think about, okay, delta square. If I renormalize delta square, and this is going to be tomorrow's talk. If I renormalize this guy, I naturally generate something that's a G2. So it became clear that you have to extend. So if you just consider these bases here, these restricted powers of delta, which is what people used to do in the past as some ansatz, you mean the first thing you can do is delta. Then you do delta squared. Then you do delta cubic. Then it becomes clear that this was insufficient and you had to include something else. And the reason why you have to include something else is because there is a symmetry in the problem, and this is GR, and you can basically have to include, you're enforced to include all operators allowed by GR. That's the most general story. Does it make sense?
Yeah, I think I'm still confused. It's probably a confusion related to the separation of scales. I thought the map between matter and the galaxy distribution was complicated and very nonlinear, so it should not be just something so trivial as this. But
so on large scales, we know that this has to be the leading correction, right? Because this is simply, you're just saying on large scales, delta has to be basically just a shift, like basically a bias shift of galaxies, because this is the first term that appears. And when you have delta square and delta is small, you basically can systematically add corrections to this. So the idea now is to start with the simplest thing, which is a linear correction, and then you systematically add corrections to this. But this is a different framework that has evolved in time. I mean, this is in the past, if you used to watch talks, people used to talk about only delta, and then people started to talk about delta square as being a correction as we slowly move towards the smaller scales. And then it became clear that this was not enough, that this, you had to add something else. And then it became clear that there is a reason for this, right? And which is the symmetry that you have, which is GR. So what we are doing here is a systematic expansion that you start on large scales in which everything is linear, and systematically add corrections to this linear story. Okay? Right, so the state of the art is that now we have many codes in the market that calculate those loops at, the one loop level, and basically take this one loop correction. I mean, you can either have in real space or what we call redshift space. You can either do field level, 2-point functions, 3-point functions, and you can also apply to different data sets and also consider different models. So in the market, I mean, nowadays it became clear that the point we stand is that this became the state-of-the-art application of, it is a framework that when DESI considered in their analysis, this was the main framework they considered when they did this full shape analysis. So nowadays, this is, you know, people involved in surveys are considering this as part of their main analysis. And the state we are is that the one loop is pretty well implemented and tested, but moving towards higher loops and smaller scales is very expensive. And this is something I've been working on, okay? So I'm gonna talk about how to push towards higher loops. So how to move to smaller scales, also including higher loops. So the future is, you can either consider higher order endpoint functions or field level contributions or other kind of statistics. People also think, since you have many operators now, you can think about priors in this kind of bias parameters, right? This becomes something relevant now. And also you can extend to different models, also different observables. And something I'm gonna explain tomorrow is what we call the RG for LSS, which is how to improve, how to gain information from higher loops, basically resumming part of the diagrammatic contributions you have. Right, okay. This was supposed to drink water, but I think I already drunk enough. So, part two, I'm gonna move towards explaining this two-loop contribution that I've been involved on, how to move towards higher loops and make them fast. So, when I think about evaluating those loops, the one-loop contribution is just a 3D integral, so you can fix one of the directions, so it's a simple 2D integral, and it takes order seconds. So it's very feasible. But when you move towards higher loops, it becomes quite expensive. So the two-loop contribution you have is a fifth-dimensional integral, which you have to solve numerically, right? And this takes order minutes. So if you want to sample cosmology, so if you want to put that inside, you know, if you want to change cosmological parameters and recompute these things, this becomes quite expensive. And recomputing these things over and over is super expensive. So the three-loop result I showed is for one single fixed cosmology, and this took us 1 week for every single K mode you evaluate. So quite expensive, right? So if you want to do it like on the fly and compute this inside a Monte Carlo sampler, this becomes impossible. So one loop is the state of the art, but pushing towards higher loops is something that we're just now in phase of being able to do that. And the approach we are using to do that, actually, this is something we released this year, is basically expanding the linear power spectrum. So those integrals are basically powers of this linear power spectrum, which is something you compute numerically, right? So this is something different than in the QFT context in which you basically have propagators and you can compute those loops analytically. Computing higher loops analytically becomes super complicated, so you have to do it numerically. And what we did, the approach we took to push towards higher loops is to expand the linear power spectrum into some bases. So we have some weights, W's here, and some eigenfunctions, V's, that you pre-compute for one single cosmological range that you have. So you basically can see that the one loop result can be written as basically products of those weights that you compute for a cosmology theta and some pre-computed tensors S. So what we have done is to pre-compute these tensors S at two loops, and basically for every single cosmology you sample, you just have to compute those weights. You just have to basically find the weights in this basis. So computing loops, once you have these pre-computed tensors Sij and Si here, becomes quite cheap.
When you do these numerics, the bottleneck is time, it's never memory, right?
So memory is never a bottleneck in this case. It's just time.
Okay, it's just time. Okay. And these computations are exact, let's say. They are numerical, but they are exact. You're not... I'm asking because I'm coming from a different field, and sometimes you can, let's say,
They're exact in the sense, I mean, they're numericals, right? I mean, you're doing numerics, right? So it means there's some numerical error like associated
right, but apart from that is exact. You're not making approximations or anything.
Nothing.
Okay.
The only approximation that's underlying everything is this space and time separation that I mentioned before.
Okay,
right?
okay.
That's,
okay.
So you can either use emulators, and this is something I've been working on with Vivian, but in this case, what we are using is just to project into this base Sij. So we pre-compute those loops, in this generic function, eigenfunctions vi. So after using this pre-computed set of eigenfunctions, you can on the fly basically compute those weights, which is quite cheap, and put that inside a Monte Carlo sampler.
So which one is faster, emulators or this?
Well, I mean, both are order milliseconds now, so it's indistinguishable. Right, so those are the results for the two loops, and this is the first time we were able to sample the two loop contributions. So what I'm showing you here is the difference between these projected bases and non-projected bases. So this is the error after using the projection. So you can see that we have a 10 to the minus 3 error all the way along at different redshifts in this projected way of computing the loops. So after using this expansion, we basically have 10 to the minus 3 error here, which is quite enough for DESI. I mean, having in mind DESI data, 10 to the minus 3 is quite good. So just to show that this projection works quite well and that we can use it. So what I'm showing here is the difference between the one loop and two loop. So one loop is in red, the red line here, and the two loop is in blue. So you see basically the two loop is able to, so this is comparing to simulations at different case. And what we see is that the two loop is able to provide a good fit up to 0.26-ish, while the one loop contribution fails at around 0.11. So this is something that allows us to basically gain a factor more than a factor 2 in terms of the scales you're able to resolve, right?
So the right is at redshift 0, right?
So this is redshift 0. Everything here on the right is redshift 0. So this means that if before using the one loop contribution, I mean, linear theory fails quite early, right? And then you add a one loop contribution. The one loop contribution fails at around 0.11. The two loop contribution in blue here fails around 0.26. So this means doubling the amount of Ks you can consider in this full shape story, okay? Also, what you see here on top is after adding the counter terms, you can basically completely remove the counter. So I'm just showing the difference between two different lambda values. And after adding the counter terms, so this is without counter terms, and this is with the counter terms. So after adding the counter terms, you can basically completely remove this lambda dependence.
So in the counter terms, do you have any ambiguity in terms of finite terms? Like, do you have to use randomization scheme or MS bar?
You have to fix a randomization scheme.
How do you do that, and how ambiguous this is? How
So
do results depend on that?
So this is the focus for tomorrow's talk.
Okay.
I can focus on that tomorrow, basically.
So I think it's the same question, but are there any free parameters you add when you go to the two? It's the
Good.
same question.
So there are many new free parameters we add. So the one loop here you see in red has one single free parameter, which is k square. So this is the sound velocity correction. The two loop contribution has more free parameters because you have to add more counter terms. And we have 4 free terms now. So the question is, okay, I can have information from smaller scales, but I'm adding more parameters. Does it compensate adding more parameters to this? And the answer to this question is yes. So what I'm showing here is the one loop result fixed at 0.11, which is the Kmax we find, and the two loop result fixed at 0.26. And we find that one loop result, basically, so those are constraints you get on AS, H0, and omega m. And you find basically the two loop contribution is able to gain a factor 30%-ish on the cosmological parameters, even after considering more counter terms in the story.
So you're marginalizing over
I'm
the extra
marginalizing
terms?
over more terms, but this still gives me more information because I'm able to go to smaller scales, okay? Here on the left, you see the figure of bias. So if you get bias or not, you see that one loop in red get biased around 0.11, and the two loop gets biased around 0.30-ish. The chi-square also works pretty well for the two loop, and the one loop fails around same scale. And this is the figure of merit, which is basically the determinant of this, of the multi-parameter correlation matrix. And you see that basically the two loop here gives more information than the one loop if you cut. I mean, it's just some details here. But you can see that the lore is that you gain more by going to smaller scales. And this is the first time we're able to sample cosmology doing a full two loop computation. Just to say, this is matter. We haven't included all the set of bias parameters. And including all the set of bias parameters is something I'm working on now, and this is expected to be finished later this year. Also, we are in real space. There's some details here. We have to go to redshift space, and the plan for the future is apply that to data. Okay? Right, so let me talk about something else I've been working on with very bright PhD students, Thiago and Francesco, which is multi-tracing. So inside DESI collaborations, we have different kinds of galaxies as well. So the question is, how to optimize the use of those galaxies? Can we use information about the galaxies, about these bias parameters to maximize the information you gain? And the answer we've been talking about and discussing is, can split those galaxies into different populations such that the bias parameters you have for those galaxies is different, and you basically maximize the information you gain. So what you see here is the power spectrum for different kinds of galaxies after doing this multi-tracer. So if you consider a single tracer, you have this black line here, but if we take one population of galaxies and split in 2 different populations, I can have different parameters of those galaxies, and this basically allows me to give, like, you see that the lines for the 2 galaxies B and A are quite different if I split them. So it means that if I'm able to distinguish galaxies by some features, I can basically disentangle the bias parameters for those different galaxy populations and use this to gain information about, for instance, AS as a function of the difference in the bias parameters you have for those galaxies. So you can see that after doing multi-tracer, we basically have a gain around 30 to 40% in cosmological parameters too. So this is considering some simulations and splitting galaxies by their colors. So we just take galaxies, split them by color, and we find a huge improvement in terms of how much you can gain. And the reason for this, I'm just flashing, you know, after having this bias expansion, you have this huge set of parameters you have to consider. So here is the cosmological parameters, and here is the huge set of bias parameters you have. So in single tracer, you have some correlations between the parameters that when you go to multi-tracer, you break basically the cross correlation between the parameters. You see this matrix here is way more diagonal, which means that splitting galaxies by their colors or some features allows you to break correlation between these multi-set bias parameters. So in the future, this is something I've been working on, is to apply that to DESI and also include the bias spectrum in this story.
Yeah, can you say more about the features you split the galaxy by, and how far in redshift can you have this information? Because I guess you are limited to very low redshift, no, if you start.
So the features, you mean the features you see here in the spectrum?
Color, metallicity, I mean, what are you looking at?
Right, so this is something we discussed. Here, you can either use color, you can use something called star formation rate, which is something you measure, like how many stars those galaxies form. And this is something that we have information about galaxies. You can use photometric information, for instance, and other kind of surveys. So you can do cross-correlation between DS to know about, you know, you take a galaxy sample and you learn about basically these galaxy features, and you use these DS data, for instance, to disentangle between those populations using some pre-computed. You can run simulations, test how close to, I mean, you can just find features based on simulations you run, and then you say, okay, I have galaxies that this kind of galaxy seems more blue, this kind of galaxy seem more red. And just finding galaxies by color, for instance, here you can see that they have different biases and different features in the power spectrum.
It doesn't help.
Luminosity also helps in this case. You can use luminosity.
Can this be applied to photometric surveys as well?
Yeah, definitely. You can use that for photometry. Like people have shown that, for instance, primordial non-Gaussianity constraints work better in the case of using multi-tracer. Also in the context of DS.
Sorry, up to which redshift you can disentangle?
So this depends. So to disentangle this, you have to have information of like extra information about galaxies, right? So depends on how different, inside one single redshift, depends how different samples you can find inside this. And you can use something, it's a bit technical, but you can use something called assembly bias to disentangle between different galaxy populations. So depends on how, the answer to this question is, depends on how different is this delta B those galaxy populations are. If you're able to find very different galaxy populations, you're able to gain information about, way more information about cosmological parameters. Okay? So let me move to another thing, which is this renormalization group for LSS. So this is going to be tomorrow's talk, so I'm going to postpone this to tomorrow, but let me just flash what introduce this team because this is something I've been working hard on. And the idea here is we have galaxies behaving in a very systematic way. I mean, you can, one question that humanity always wonders about is how things change as a function of scales, right? And you see here a broccoli that if you zoom in, you find another broccoli inside a broccoli inside a broccoli, right? And galaxies are actually a bit different. You don't have this self-similarity, but you see that galaxy field evolves. I mean, as you zoom in, you still find some similarities between how the galaxy field on small scales is on large scales. So the question I'm going to try to address is how galaxies, how the description that you have for galaxies change as you zoom in your galaxy field. And in the context of quantum field theory, the equations that describe this is what we call the renormalization group equation, or the Kalan-Semantic equation. So in QFT, we have how a coupling G evolves as a function of the cutoff lambda. And what we have developed is we generalize this equation to the context of galaxies. So here, the Hall coupling constant change as a function of lambda is given by the beta function of this theory that you have. So in the case of galaxies, as I was mentioning, the analog of the coupling constants that you have are the bias parameters. So you can ask yourself how the bias parameters change as a function of scale, lambda, and this is given by just a linear combination of these other bias parameters, B, B. This S here is just a matrix, and what determines how fast things change in galaxies, like in the case of galaxies, is how large the variance of this field is. So the galaxy field has an intrinsic amplitude, like the power spectrum has an intrinsic amplitude of those fluctuations, and depending on the size of those amplitudes, basically the RG is going to be faster or slower. So this is the variance of the linear density field. And the amazing thing about using this kind of technology is that I'm showing here how B delta evolves as a function of lambda, and you see that before we used to have, I was talking about this loop expansion, and you can think about each one of those loops adding a sigma square contribution. Basically, you're going to higher orders in fluctuations. So you see here that every single order you go, like in sigma square, is basically accounts for going to extra loops. So here is just the tree-level contribution in yellow, and if you add the one loop contribution to the bias, you see that you go to this orange curve here. And then if you add a two-loop contribution, you go to this red curve here. And what the RG does for you is to resum part of these contributions. So this is what happens here in this black line. So the RG solution basically resums part of higher loop contributions that come from higher powers of sigma square contributions. More details on that tomorrow, but the question is how useful this RG story is. So when we resum higher loops, the question is we're resumming part of those loops. Is this part large enough compared to the part you're not resumming? And what I'm flashing here is the one loop and the two loop contribution. And you see that the two loop contribution, the intrinsic two loop RG contribution, is actually small compared to the one loop contribution. So this means that what the RG does for you is to resum the main part of higher loop contributions. And this part that sticks to the higher two loop RG is actually small compared to the one loop RG part. So again, more on that tomorrow, just to flash the result. So we have this equation, and the question is, does it work? And this is something I've been working on. So Harry is a master's student I'm supervising, and what we are doing is to measure how those bias parameters change as a function of scale. And the solid line here is the RG prediction that we have. And you see that basically all the points that you measure in simulations match quite well the RG prediction. So it tells us this is about to appear. Harry is finishing the paper now, and we see that it matches quite well the prediction that we had. So the RG, the equations that we have that describe how the bias change as a function of scale exactly match what we expect. More on that tomorrow, so another pause to drink water. How much time do I have?
Well, you started at 10:35. You can obviously go over time because we have lots of questions.
Okay, good. Okay, let me switch gears and talk about cosmological tensions. So I mentioned earlier today that we have many tensions popping up in cosmology. I'm gonna specifically focus on one of those tensions. So this here on the x-axis, I'm not showing, but it's H0, so the value of the Hubble parameter. And we see that there is a tension in between CMB values that you see here. So CMB values are basically here on the left. And what do we measure with supernova here on the right? So many different measurements coming from supernova give us higher values of H0. And you probably wonder about if H0 is still around as a tension after GAWST results. So there was some discussions going. I think this is something, definitely H0 tension is still around, but we are waiting for GAWST results to verify this, so you can check recent Adam Rees papers on these H0 results. So sticking to the H0 tensions, we should, as a theorist job, we should think about simple models that can address this tension. And I've been working on, I have a couple of works also thinking about which kind of models can address this tension. And one model, one quite simple model we have in mind as a theorist is to just think about gauge theories, right? So when you think about dark matter being gauged, so we have a dark matter field psi here that's gauged under some dark SUN. And if you have a symmetry breaking, in this case, that brings this SUN down to SUN-1. So here we have dark matter, and then we have a scalar field. Basically, we have a phase transition in this case, that generates enough energy in this scalar sector and injects a lot of energy in this early universe plasma. And this is something that we have seen. So what we see here in green is lambda CDM. And when we think about, okay, is it able to bring us to higher values of age? Of course, lambda CDM gives us lower values of age. And when we consider this model, this dark SUN, we find that we're actually able to bring the typical value of age not like to higher values, towards higher values. In this case of modeling, and the tension goes down from 5.7 sigma to 1.4 sigma-ish.
Sorry, Henrique, this is like early dark energy models?
So this is quite similar to early dark energy in the sense that you have a phase transition. I mean, in the case that you have a scalar field that undergoes, that injects a lot of energy in the plasma. But it's different in the sense that this early dark energy, I mean, this phase transition happens quite early. So the solution in this case is that you generate a dark radiation sector. So what happens here is that you have a phase transition, and the scalar field basically injects a lot of, like, basically reheat the plasma, generating dark radiation. So this resembles both, this has features of EDE, early dark energy, but it also has features of dark radiation because you have a plasma and you inject enthalpy in the plasma such that you have extra dark radiation components.
Wait, how early? Before the nucleosynthesis?
So this is the point. It's after nucleosynthesis. So what I'm showing here is exactly when it happens. So I'm just flashing here the amount of dark radiation. I mean, the energy component as a function of time. So A here is basically the scale factor that you have. And the required, basically, one typical solution for age not tension is to add some extra dark radiation species. But extra dark radiation species are in tension with BBN, as Ricardo pointed out. So BBN is here. So in the model we have a phase transition that happens after BBN. So in between BBN and the scales like recombination, the scales of recombination, we have 10 to the 6 factors of A. So this means we inject enthalpy in the plasma after BBN, so you don't violate BBN, and you basically reheat this dark sector after BBN, generating these dark radiation components. Before CMB decoupling.
And what's the contribution to N effective?
So the contribution to the N effective is order 0.3-ish, so it's still allowed by CMB. And we find that after adding this extra delta effective 0.3-ish, which is allowed by CMB, and adding this dark matter that's gauged under this field, you're actually able, like this interaction between dark matter and dark radiation allows you to basically give a very nice and smooth feature that's able to give, it's a good, we still have, we're still around 2 sigma-ish Hubble tension, but from 6-ish to 2-ish, so way better. Not much, actually. So still, this of course is a free parameter of the model, right? This depends on exactly how much dark radiation you have. But this is the solution you have, right? So one typical solution is to delay this equality, and this is what happens here.
So is there any way to check if this model is correct? I mean, so maybe it reproduces what you want for the tension, but how do you check if this model
So the question is how to test with new data, and we have a lot of new data coming. I mean, ACT just released their new ACT, is this experiment, like CMB experiment, on the ground, and they're actually able to measure very small scales, and they give good constraints on extra delta and effective. So this is something that we're going to be able to distinguish soon in the future. So we are working now on using ACT data also to test this model. So this is not a crazy model that, I mean, this is going to be either ruled out in the short future or not.
But also in terms of predicting the abundance of this dark matter. So you have a dark matter candidate, so you can predict the abundance?
So as Rogério pointed out, okay, we have these, okay, sorry for going back and forth. We have a dark matter candidate that interacts with dark radiation, Xi here, and we assume this dark matter has been around since BBN. So this is the only thing we have to assume, that dark matter is there. So there is no prediction. We're not talking about generating dark matter here. We're talking about a dark matter that has been around and interacts with this dark sector.
And for detection, direct detection, do you have any?
Of dark matter?
Yeah.
So these change, only a fraction of dark matter, and this has some bounds. This interacting sector adds some bounds, but since we are not exactly, we're not coupling to the standard model, right? So it's so this is a completely secluded dark sector. So we're not talking about. Right, so we see here that the tension goes down from 6 sigma-ish to 1.7 sigma-ish, so quite good. So after adding supernova data, also our model, which is in blue here, seems like to have a good agreement with SHOES data, supernova data. Right, so one specific feature of this model is this after symmetry break. So dark matter here, when you still like in the symmetric phase, dark matter is basically like fully gauged under this dark SUN. And when you have a symmetry break, you have two dark matter particles, like one that's still gauged under this new dark SUN -1, and one that's basically neutral, this size 0 here, which is neutral. So one specific feature that comes naturally in this model is that after a symmetry break, if you have this phase transition, you basically have a mass split that's generated by loops. So one of these dark matter particles is actually slightly more like massive, has slightly more mass than the other state. So this means that if you have temperatures around this mass split delta M, one of these basically particles basically goes to another, like to the neutron state. So it means that dark matter that was interacting naturally stops interacting when the temperature of the universe reaches around delta M. So this means that in this dark sector, basically, dark matter that was interacting smoothly turns off like this interaction and goes to usual CDM story. So those are the constraints that we get. So do we see that this huge region here that allows for large values of age, and as delta N effective increase, as was asked basically to order 0.5-ish, we're able to reach age values that are actually allowed and like by SHOES data. Just to say that another feature of this model is that since you have a phase transition, in this phase transition story, we can think about gravitational waves. And we're, of course, very excited about gravitational waves in the context of pulsar timing arrays. So I'm just flashing here nanograph results and SKA results, so what to expect for SKA. And we see that basically nanograph like has just this amazing stochastic 3 sigma-ish detection, like that was released last year with nanograph 15. And in our model case, there's some parameters of our model that actually slightly touch nanograph region. So if you have this phase transition happening quite early in the universe, you can actually have some, agreement in between like what nanograph expects and our model. So just to say that this is a feature, and this brings me to a smooth transition to the next topic, which is gravitational waves.
So before a smooth transition, I want to ask about this phase transition. Is it smooth? Is it first order or second order?
It's a first order transition. So the idea is that you want to inject a lot of energy in the plasma, and I mean, it doesn't have, it's not necessary to have, but you have to have something called like supercooling, in which you inject a lot of energy in the plasma quite quickly. It's necessary for us to generate like.
But do you have any requirements on the gauge group in order for, or the amount of fermions that you have?
Yeah, we do. We do have some constraints. We add those constraints to the paper. I don't know. I cannot quote the numbers now, but you have some constraints on the gauge groups you are allowed, and you cannot. I don't remember the numbers. I'm not going to say, but yes, we do discuss this. So just to say that when you have a transition, when you have a first order phase transition, you can generate gravitational waves, and this is something I have also worked on. So gravitational waves from phase transition is something that has been around, for many, many years, that people have discussed this. So what I've been working on is to construct simulations that predict how much gravitational waves form like in these phase transitions. So what you have here is a simulation that has a fluid coupled to basically a scalar, and what we resolve here is the fluid part. So we are focusing on the fluid part, and the fluid, when you have a phase transition that couples to a fluid, you generate like sound waves in the plasma. Those sound waves propagate for long, long times. And those long times that those sound waves propagate for generate, like these kind of structures of bubble colliding and basically sourcing gravitational waves. Just to quickly go through phase transitions, so if you have a false vacuum and if temperature goes down in the universe and at some point you go from like a false vacuum to a true vacuum, you generate these kind of bubble structures in which part of the universe is in the symmetric phase and the other part of the universe is in the true vacuum. So it means that at some point, like those bubbles they can grow, collide, and they can source gravitational waves. So for many, many years, people have focused on gravitational waves from the scalar field itself. So if you have a scalar field, at some point, those bubbles of scalar field can collide and generate gravitational waves. And people have computed the gravitational spectrum in this case. So just to show some results of what we call the envelope approximation for this kind of calculation. But later it became clear that if you have a thermal universe, so if you have a plasma in which like this phase transition happens inside this plasma, you can actually excite this plasma, generating waves in this plasma. So it was pointed out by this paper in 2013 that actually the fluid contribution, if you have a fluid, can actually be larger than the scalar contribution phi here. So actually, if you have a fluid coupled to this scalar system, you're going to generate waves for long, long times. As you see here, the scalar part decays while the fluid part goes on for long, long times. So the question is, how can we predict gravitational waves from this fluid component? So one thing is to use the envelope approximation for the scalar part, but for the fluid part, it's a very non-linear system. So what I'm showing you here is that if you have a phase transition Lagrangian, I mean, you think about the fundamental Lagrangian, you can embrace this in this fluid system into some thermodynamical parameters. Just to flash here, you can have, for instance, like some of those parameters are the strength of this phase transition, the size of this bubble, the bubble walls, like how fast those bubbles move, and also the temperature of this plasma. So if you want to actually be able to constrain with PTA or LISA or like with LIGO, how much like those experiments like constrain phase transitions, we should be able to predict come from like fundamental physics to gravitational waves. So how to predict how much gravitational waves form. And this is a strongly non-linear system because you have fluids like strongly, like a lot of energy injected into the fluid that basically propagates, and this fluid like evolves, collides, and sources gravitational waves. So the question is how much gravitational wave you generate. And this is something I've been working on, and we have developed what we call the Higgsless scheme to predict how much gravitational wave you have in the fluid in this case. So one challenge in this case is to have numerical simulations because you have a very non-linear system, so you have to construct numerical simulations that are actually able to resolve the shock structures that you have. So you form shocks in the fluid, and those shocks propagate for long, long times. So how can you keep track of the shocks numerically and predict how much gravitational wave forms? And we have developed what we call the Higgsless scheme, in which we basically evolved only the fluid part, and all the Higgsless, I can talk more about that if you want, like, but it is that you integrate out the Higgsless, like the Higgs part, so you integrate out the scalar part, focusing 100% in the fluid part. So this allowed us to actually run tons of simulations to predict Q here. Q is the gravitational wave spectrum as a function of frequency, and what we have seen is basically this double broken power law structure, and we have run tons of simulations for different cosmological parameters. So here is the strength of the phase transition. Here is the wall velocity that you have. So we basically fitted the shape of this gravitational wave spectrum. So we basically fitted the position of the peaks, the slope of the peaks that you have, and we have seen how much actually you can go to the strong phase transition regime. So for the first time, we're able to go to strong phase transitions. So what you see here are results for the simulations that we had for very strong phase transitions. So alpha 0.5 means that 50% of the energy of the scalar sector is injected into the plasma, a lot of energy like in the plasma. And those waves propagate, like those sound waves propagate, generate phase transitions. And what we see here is that for weak transitions, intermediate transitions, and strong transitions, how those waves decay. So we have measured this, what's the typical decay time for those waves in the plasma. And we came up with something that's a very simple shape fit for the gravitational wave spectrum that people can use. I mean, people can just use these shapes that we provide and test that against LISA or PTA or whatever you want. So it's a very simple way, very fast and very accurate way to how much gravitational waves form in this early universe system. So here are just some slides of our simulations that we have. And so, yeah, just to wrap up and conclude, so I think we're in the era of having a lot of data coming either from gravitational wave side or galaxy clustering, like, or general, like a large scale structure. And I think it's a good time to actually work on the interface between those topics because there's a lot of methods that we can use to systematically get more information from either galaxies or gravitational waves or whichever probe you have. So to conclude, thanks.
Scott, did you have any questions?
No, I asked them during the talk. Thanks.
Can you go back 2 slides?
Which one?
Just the one with the, yeah, no, 2 slides only from this one.
This?
Just, number 55, 56, sorry.
Here?
Yeah, right. So you have a scale there, Q0 basically, right?
Yeah.
You have 2, 1, 2, 2, but actually Q0 is doing most of
Yeah,
it.
thanks for...
So what's in that scale? What gives you, is this something by dimensional as you can get something like this? Or?
Yeah, so I mentioned that in the past, people were mostly concerned like with gravitational waves from the scalar part, right? So when you think about the scalar sector forming gravitational waves, you have one single scale, which is the typical size of the bubbles when they collide, right? And you have a gravitational wave spectrum. Okay. As a function of frequency, which has a peak exactly in this typical 1/r scale, okay? In the case of fluids, actually when you have a fluid, when you add fluids to the story, like when you have a phase transition and you have a fluid, basically you have something else, which is, if you see the simulations that we have here, they have something else beyond the typical size of the bubble, which is the thickness of those bubbles, right? So you see another scale, which is how thick those fluid profiles are. So if you have a fluid around those bubbles here, you're going to have basically, okay, I'm just zooming in one of these region here. So if you go like, okay, as a function of, okay, here. As a function of the radius of the bubble, you have something like a velocity profile and have like these shocks forming, right? So you have something else that's beyond just the typical R scale that you have here, but you have something like, which is the typical width of this fluid profile, sigma, if you want to have something like this. So instead of having just this simple peak structure, you're going to have something else, which is this double broken power law. And beyond this 1/r scale, which is still imprinted on large scales, okay, this would be 1/r. But you have another scale, more in the UV, which is the thickness like this, 1/sigma scale. And this is something that with our simulation, since we have this very fast and accurate scheme, we are able to resolve the structure of this peak by running tons of simulations. You can actually get exactly these double broken parallel positions of the peak. So we are able to very precisely pinpoint exactly where this double peak, the second peak is. So to say Q1 and Q0 are those 2 positions.
So I had the maybe philosophical question, but you're always comparing your theory with some simulations.
Yeah.
So the simulations have some built-in, what do they assume the simulations? Is it just general relativity and matter and nothing else? Or?
So in the case of dark matter, I mean, we have 2 kinds of, let's say, 2 general class of simulations. We have dark matter only simulations in which you plug in particles and decouple via gravity. I mean, that's just gravity only simulations. But you can add also hydro simulations. And then this also turns on this tracer mode. I mean, you basically add tracers and you can find galaxies in these hydro simulations as well. So there are 2 kinds of simulations in the market. If you have matter only simulations, you can test basically the matter part, which is the first part I was describing. But we also have classes of simulations which are way more expensive, which also evolve basically some, they have some phenomenological baryonic modeling for how particles interact beyond gravity.
Yeah, that's what I was asking. So it's not like, so it's like ab initio, you would say, and the first one is like ab initio. It's just fundamental forces and that's it. Is that right?
The first one is just gravity. You never like a
nothing phenomenological. It's just
no. I mean, for the gravity, for the dark matter only, it's just Newtonian physics, right?
Okay.
So, and then you can do something more complicated, which is hydro.
Okay,
but this is way more expensive, and you can only normally do smaller boxes compared to what you would do in like in the case of dark matter simulation.
Okay. Other questions? Okay, so let's thank Henrique.